In this question, we're taking everything we've learned about covalent compounds and putting it all together. Our first step is to draw a Lewis diagram for the compound in this question. Here it's CSE2. So my first step now is to go to the periodic table and figure out how many valence electrons I have on carbon and selenium. So firstly, carbon. Here's carbon in the periodic table. And then selenium, Se. Here is selenium. So carbon is in group 14 and selenium is in group 16. So according to our shortcut, that means that carbon has 4 valence electrons and selenium has 6 valence electrons. So going back to our question, we have carbon, which has 4 valence electrons. We have selenium, which has 6 valence electrons. And in our compound, we have CSE2. So we've got 1 carbon plus 2 seleniums. So that's 1 times 4 valence electrons plus 2 times 6 valence electrons, which is a total of 16 valence electrons. Okay, so now when I go to my diagram, first I'm going to add a single bond joining my atoms together. So I've got 2 single bonds drawn there. Each single bond is made up of 2 electrons. So I've used up 4 electrons now. So I want to keep a running total. I started with 16 valence electrons. I've just used up 4. So that gives me 12 valence electrons remaining for now. Next step is to add electrons on my outer atoms. I've got 12 valence electrons to add. So I'm going to add 6 valence electrons on each of my outer atoms. So now that's 6 electrons twice, which is 12 in total. I've used up 12 electrons there on my diagram. I have 0 valence electrons left to add. So I now have all my electrons on the diagram. My last step is to check that the octet rule is being followed for each of my atoms. So first, looking at this selenium atom here, I've got 1, 2, 3, 4, 5, 6 total electrons plus 2 electrons that are in the covalent bond. So that's a total of 8. So the selenium atom on the left is looking good. That's obeying the octet rule. The selenium atom on the right is exactly the same. We've got 6 electrons in lone pairs and 2 in a covalent bond. That's a total of 8. So this atom is also obeying the octet rule. Now my carbon atom in the middle has 2 single covalent bonds, which each contain 2 electrons. So that's a total of 4 electrons. So my carbon has 4 electrons around it. It needs 8 to obey the octet rule. So right now, carbon is not obeying the octet rule. So to fix that, what I'm going to do is take a pair of electrons from my selenium and form them into a bond. So I'm going to form that into a double bond here with my carbon. So I moved that lone pair and formed it into a double bond. And I'm going to do the same thing on the other side. So I'm going to take this pair of lone electrons, form that into a double bond there between my carbon and my selenium. And now if I recheck my atoms, this selenium has 2 pairs of lone electrons plus a double bond. So that's 1, 2, 3, 4 electrons from the lone pairs, and then 4 from the double bond. That's 8 in total. And this selenium atom is exactly the same. We've got 4 electrons in lone pairs plus 2 double bonds, which each contain 2 electrons. So both of my selenium atoms are now looking good. They're following the octet rule. Lastly, for my carbon, I've got 2 double bonds. So that's a total of 4 covalent bonds formed. Each covalent bond contains 2 electrons. So that's 8 electrons in total. So finally, I have the correct Lewis diagram there with all of my atoms obeying the octet rule and the correct total number of electrons. So that was step 1, drawing the Lewis diagram. If you need more help with that, go back to the previous unit, Introduction to Covalent Compounds, and practice some more there. Now the first questions here ask me to find the shape and bond angles of this molecule. So to do that, I have to look at my central atom, which is the carbon atom here, and count how many electron domains I have. So this double bond here, that's 1 electron domain, and this double bond here, that's 2 electron domains in total. So going to look at my reference sheet, I have 2 electron domains, and I have no lone pairs. So I have a linear geometry, and my bond angles are 180 degrees, and you can see there the shape of the molecule is linear. So to answer those questions here, the shape is linear, the bond angles are exactly 180 degrees, and from my image choices here, A shows a linear molecule. Next, it's asking about hybridization. Remember, with hybridization, we're looking at the number of electron domains again. Here we have 2 electron domains, so that tells me that 1 s orbital and 1 p orbital have been hybridized together to form 2 sp orbitals, and we have 2 regular p orbitals as well. So the type of hybridization here is sp, since we only have 2 electron domains. Next it asks, does this molecule have free rotation? To answer that question, we need to look and see, do we have any double or triple bonds, since they contain pi covalent bonds, which don't allow free rotation? And the answer is yes, we have 2 double bonds here, so that means no free rotation. The answer is no, and the reason why is that there are pi bonds present, and pi bonds do not allow free rotation. Lastly, we're looking at our electronegativities of our elements. It tells us carbon has an electronegativity of 2.55, and selenium also has an electronegativity of 2.55. So it's asking us, is this a polar molecule? So we've got 2 steps to that. Step 1 is asking us, are the bonds between these atoms going to be polar? Now, since carbon and selenium have the same electronegativity, the difference in the electronegativity here is 2.55 minus 2.55, which actually equals 0. So our electronegativity difference is 0, and we have a rule that if the electronegativity difference is less than 0.4, then we have non-polar bonds. So here, since the bonds are non-polar, we know the whole molecule has to be non-polar. So the answer is non-polar. The second thought regarding a polar or non-polar molecule has to do with if the molecule is symmetrical or not. Now this molecule is symmetrical since it's linear in shape and we've got the same elements on both ends. However, that doesn't matter regardless, since we've got no difference in electronegativity and the bonds are non-polar. That means the whole molecule is going to be non-polar anyway. So the answer is the molecule does not contain any polar bonds, and therefore the molecule must be non-polar.